We're going to continue with section 6.3 and talk about de Moivre's theorem. So consider a complex number z in polar form, uh, which will be written as z is equal to r cos theta plus sine theta I. So if n is any non-zero integer, then z to the power n is equal to r to the power n times cos n theta plus I sine n theta. So if we think about the multiplication, the definition of multiplication of a general complex number, then we will see that if we are to take powers of complex numbers, this would definitely be easier than the first definition that we had. This will definitely be easier to work with because we are just going to say r to the n, and then we multiply the theta that we had by n, and then we have our answer, right? And let's look at the proof. So we prove the result for n greater than 0. Then the case when n is less than 0 is given as an exercise, and that is exercise 6.3 number 5. So because we said any non-zero integer, so we are going to look at positive integers, and then for negative integers, that's an exercise in the textbook. So we know that for n is equal to 1, this is going to be true trivially, because z to the power 1, which is equal to z, is equal to r cos theta plus sine theta I, and this is just coming from that, which we can then write as r to the power 1 cos 1 times theta, so plus sine 1 times theta I, expressing it in this way. So therefore the case for n is equal to 2 is true, right? Let's look at, so here we are using I'd forgotten, we are using the principle of mathematical induction to prove this theorem. So we have proved it for n is equal to 1. Now suppose that we fix an integer k which is greater or equal to 1, and assume that the result holds for k, and we want to show that if it holds for k, then it has to hold for k plus 1. So then if it holds for k, then what it means is z to the k is equal to r to the k times cos k theta plus sine k theta I, right? And now we know that by theorem 6.3.6 we proved a way of multiplying two complex numbers in which are in polar form. So z to the k, we know, sorry, this is supposed to be z to the k plus 1. So z to the k plus 1 is equal to z to the k times z, which if we write it in polar form, so we know that this is true, so therefore we put our inductive assumption here, times z, and that is z. And then so here we then say, okay, r to the k, so now we are using theorem 6.3.6 here to say if this is the case, so if we are multiplying this by that, then we are told that we are supposed to say r to the k times r, so we are multiplying the two r's here, and then for the angle, we know that we are supposed to add this one plus the angle on the other complex number, so that's where the k theta plus theta is coming from, and that is equal to, so if we then simplify that, then we get r to the k plus 1, right, from here, and then we also get cos k plus 1 theta plus sine k plus 1 theta I. Here we just factor out the theta in there, and then we get that. and so z to the k plus 1 is equal to r to the k plus 1 times that. So therefore, if z to the k plus 1 is equal to r, sorry, z to the k is equal to r to the k plus that for some fixed but arbitrary k, then this happens. This means that by the principle of mathematical induction, our statement, our original statement is true for any integer that is greater or equal to 1. Right, so that is that for that proof. So we have shown that de Moivre's theorem is true. So that gives us a way of multiplying. So we're going to look at two examples, and this is example 6.3.10. So within the example there are two questions. So for z which is equal to 1 minus I, we calculate z to the 9 and z to the minus 5, and we write the answers in standard form. So the polar form of z is equal to z which is equal to root 2. So here we find r, and then we find the principal argument, right? And then so it comes out like that. Now therefore, by de Moivre's theorem, which is theorem 6.3.9, z to the 9 becomes z to the 9 over 2, because here this is 2 to the half, so we just say 2 to the half times 9, and then we get that. And then inside we also multiply 9 by the angle inside there, and then we get minus 9 pi over 5, like that. And then for here we then say we want to get the principal argument, so we can see that this can be written as minus 2 pi minus pi over 4, and then minus 2 pi minus pi over 4 there, and we can remove the multiple of 2 pi, that one, right? And then we are left with minus pi over 4 inside there, and 2 to the 9 over 2 is equal to 16. We can easily check that. So we can check that that is true. Maybe not quite, but anyway, if we look for cos minus pi over 4 and sine pi over 4, whatever we get we multiply by that, and then we get that the angle is 16 minus 6i. Right, let's look at the other question, z to the minus 5. Right, what does it say? It says if we use de Moivre's theorem, then we have z 2 to the minus 5 over 2, and then we multiply this angle minus pi over 4 by minus 5, and then we get cos 5 pi over 4, and then they also cos pi over 5, cos 5 sine 5 pi over 4. And then so if we simplify that, well, if we write it, so we can see that 5 pi over 4 is not between minus pi and pi. So what do? We express this as 2 pi minus 3 pi over 4, and then we can always remove the multiple of 2 pi because it doesn't affect the angle here, and then we are left with minus 3 pi over 4, which is between minus pi and pi, right? And then if we do the calculation, we'll simplify that, we then get that this is minus 1 over 8 minus 1 over 8i, which we can write as I over 8. Right, so that is that for de Moivre's theorem. You can look at the questions in the textbook to solve to get more exposure on this, but otherwise this is the idea. Thank you.